just a brief mention of what we did last time. Last week we were looking at the Fourier series of even and odd functions. And we also introduced in section 3.4 there the notion of half-range series. So if you were only interested in a function on, say, the positive half of the interval, you can kind of dictate what type of Fourier series it has, in the sense that you can make it be a series consisting all of sine functions or all of cosine functions by supplying the definition of the function on the negative half of the interval and thus making it a even or odd function, okay, by how you define it on the negative half of the interval. So that idea is called the idea of a half-range series. So if you just want to pick up the behavior of the function across one half of its range, say from 0 to pi, you can simplify it in the sense of arranging that the series be only sine functions or cosine functions. Now, we just got a couple of lectures left, really, in this chapter, and to finish off the topic of Fourier series, I'm going to do this section 3.5 here in the notes, which is the last section in the printed notes that you already have. But I've still got another lecture or two for next week on where you take this material afterwards. So next week I'll give you a little introduction to the Fourier transform, which is kind of a continuous analog of the Fourier series that we're seeing here, okay? And that is one of the main tools used in signal processing. So in the third year unit on digital communications and sound processing, can't quite get that out. Sound processing. The Fourier transform is one of the main tools that's applied there. So I'll give a little bit of an introduction and show how the Fourier transform can be constructed or obtained from what we already have here from the concept of Fourier series. But for today, we're coming back to section 3.5. Yeah. So what do we have in section 3.5 here? Well, we start off with a little bit of a illustrative example, and the example is incorrect. It's meant to be. It's demonstrating something that happens when we make a certain assumption about the Fourier series, which in this example isn't true. And then we'll discuss what's going on there, and well, we'll introduce the notion of different types of convergence for sequences of functions and reach something called Parseval's theorem. So the example we're going to look at just starts off by considering the function f of x equals x. Okay, so this is the quite straightforward function. It's just f of x equals x between pi and minus pi. So it's just its graph is just the line of slope 1. So that's an example we've worked with previously, and we found that it had a Fourier series consisting of sine functions. That's it there in 3.26. Okay, so it's an alternating sum of sine functions. It's the minus 1 to the power n plus 1, and it's kind of got a alternating harmonic series coefficient in front of the sine functions, 1 over n. So that's it written out there. Sine of x minus a half of sine of 2 of x plus a third of sine of 3 of x, and so on. Now consider for a moment if we were to differentiate the Fourier series. Well, differentiating the left-hand side is easy. On the left-hand side, you just have x. So differentiating that with respect to x just gives you the constant 1. And suppose that we could go ahead and differentiate this infinite series term by term, meaning form the infinite series of the derivatives of each of the terms of the original Fourier series. So what would that look like? Well, that would look like 2 times, well, the derivative of sine is cosine. So you'd have 2 times cosine of x The derivative of sine of 2x is 2 times cosine of 2x, and then the extra factor of 2 you get at the front would cancel the half, and the extra factor of 3 you get at the front here when you differentiate sine 3x would cancel the third, and so on. So what you get on the right-hand side will be 2 times the cosine of x minus cosine of 2x plus cosine of 3x, and so on. However, is this a valid series expression? Well, I mean, what's represented here on the left-hand side, okay, is the number 1, but it's kind of really should be the constant function 1 across the whole interval minus pi to pi. So we can think of evaluating these two functions, say, at x equals 0. If you evaluate them at x equals 0, you get a rather strange result that supposedly 1 is equal to 2 times 1 minus 1 plus 1 minus 1 plus 1 minus 1, on and on and on. Well, it says in the notes that's plainly nonsense, and it kind of is. On the left-hand side, you've just got a constant 1, whereas on the right-hand side, you've got this divergent series, or it's not a convergent series. It's a series which is alternating in value from 1 and 0. Okay, isn't that it? 2 times 1 minus, or 0, sorry, 0 and 2. It's alternating in value from 0 and 2. So we would normally not regard those two being equal. Fixed constant 1 and a flip-flopping, or an infinite series with a flip-flopping partial sums. Okay, alternating between 0 and 2, 0 and 2, 0 and 2. So the question is, well, what has gone wrong there, or you know, what led us to this seemingly nonsensical result? Well, what led us there was this assumption that we could differentiate the Fourier series term by term. This assumption that we were allowed to do this, to differentiate the whole infinite series, to do that by differentiating each bit of the sum and adding up all the derivatives. So there's a problem with that. That isn't actually a valid operation. So here in equation 3.3 is a kind of is what we supposed we were able to do. The derivative of the infinite series was the infinite series of the individual derivatives. Now, the problem arises here because of the infinite nature of these sums. There is absolutely nothing wrong. There is nothing wrong with saying that the derivative d dx of a finite sum of some functions, whatever they are, there's nothing wrong with saying that the derivative of this kind of sum is the sum of the derivatives. Okay, there's nothing wrong with that. That is correct, assuming those functions f have derivatives, assuming you're able to differentiate. Sorry, let's put a label, fn of x. So we got a sum of different functions, just as in here we got a sum of the sines. So we got a series of functions here. Well, there's nothing wrong with this in a finite setting, because this is just the extension of the results, which is the linearity of the derivative. Okay, one of the first things we proved about differentiation in first year was that d dx of, say, f of x plus g of x, the derivative of a sum of two functions was the sum of the individual derivatives. That was one of the first facts or theorems about differentiation that we proved in first year. And you just need to repeatedly apply this to reach any kind of finite sum. Okay? Because a finite sum is really just a finite collection, or just a bunch of additions of two functions like this. You just keep on adding on a new function each time, just keep on building up the sum until you reach the finite sum. But of course, you can't automatically extend that to infinite sums, okay? Because you will never reach an infinite sum by just repeatedly applying this fact about the linearity of the derivative of two functions. Okay, so it cannot simply be extended to infinite sums. Infinite sums of functions. And the reason being, and the reason we're going to explore now, and I'm going to tell you about now, is that infinite sums of functions can have different forms of convergence. And it's these different forms of convergence which is one of the things which says whether you're allowed to differentiate them term by term or not. Okay? Okay. So I need to tell you a little bit about types of convergence. Types of convergence for sequences of functions. Now, the setting we're going to be thinking about this is we're going to consider the partial Fourier series, or the partial sum. Consider the partial sum Fourier series f of m. We'll call it f of m, a subscript of f of m. And f of m, or fm, is just the partial sum up to the mth term, so you sum from n equals 1 to m, of the infinite Fourier series. So we have an cosine of nx here, plus the sum from n equals 1 up to m of bn times the sine of nx. So it's this m here, is that m there. Now, the idea is, which we've been talking about all the time, is that so such a thing would only be an approximation to whatever the objective function f you started off considering was. It's just a sum of the finite number of the terms of the Fourier series. But when you take the limit, when you include the infinite number of Fourier series terms, then you get exactly the function that you were starting off with. Okay. So we're considering this kind of thing, and this is the way we've been talking about these, is that these converge to the limit function f. F of x. So you have this idea that the limit as m goes to infinity of this partial finite Fourier series function is equal to whatever the original function we started off with. But it turns out that there's different ways in which you can have sequences of functions converging to a limit function. Okay? Different ways in different types of convergence here. So it's in this limiting process here that you can have different types of convergence. So the different types we're going to talk about is, the first one is pointwise convergence. And the second one is uniform convergence. And the way, just before we get into saying what they are, just to kind of know some idea of them, is pointwise convergence is a kind of weak kind of convergence. And uniform convergence is a stronger type of convergence, or a more well-behaved type of convergence. So, you know, it's a lot harder for a sequence of functions to be uniformly convergent. It places a lot more restriction on the behavior of the functions. Okay? So it's a more specialized type of convergence. But because it's more specialized, it behaves better in a way that I'm going to tell you. Now, just to be clear here, and I'll show you, we'll go back to look at one of the illustrations of a Fourier series, which we used before. I'll just find it here. This one here. Okay, so you'll recall this kind of picture, which we used as one of our first examples for exploring Fourier series. So here we had the original function, which we call the square wave function, or it's really the Heaviside step function over the interval minus pi to pi. That's the function graphed in red there. So it's a very simple function. It's just equal to 0 in the negative half of the interval and equal to 1 in the positive half of the interval. Then in blue there is a Fourier series approximation to it. So this is the one containing, so this slider here is the number of terms, okay? The number of terms m involved in the Fourier series approximation. So if you slide it right back down to 0, you have just the constant, the Fourier series consisting of just a constant. So that's the constant z. That's the constant, a half. That's the best approximation, best constant approximation to the square wave over the interval minus pi to pi. Now, as you increase the number of terms, the blue function, the Fourier series approximation, is getting closer and closer to the square wave function. It's converging to the square wave function. Okay. But you see, this convergence has to happen along the whole domain. Okay? So the difference between these two types of convergence here is describing that it's related to this idea that if the functions are converging to the limit function, well, they have to converge at all the values across the domain. So it's about how the sequence functions do that convergence. Okay? So let's get into some details here. So this is the pointwise one. Pointwise convergence. So this is when at each value x in the domain, we have that the value fm of x converges to f of x as m goes to infinity. Okay, that's what we want. We want the function values at any particular point x to converge to the function value of the original function f. But crucially, this convergence can happen at different rates. Different rates or speeds, if you like, different rates or speeds at different arguments x. I'll be able to illustrate that in a moment with this square wave function example. Formally, the formal definition of pointwise convergence would be for every x and for every epsilon, there would exist some point capital M such that for every m greater than or equal to the capital M, the absolute value of f of m of x minus f of x would be strictly less than epsilon. Okay, this is just putting formally into symbolic logical language the statement described in the preceding paragraph. But the key point to be aware of is the relative position of this universal quantifier over the variable x and this existential quantifier there, which is kind of to do with the rate of convergence. So this says, well, you know, at every point x in the domain, or you can find such an m, such that if you wait until after that point in the sequence of functions, the function value in the sequence, fm of x, will be within distance epsilon of f of x. But there's no requirement here for the same m, the same capital M, to be working for every x in the domain. It's because the quantifier over x is given first. So for every value of x in the domain, you can find such an m. And this example here illustrates this idea of the convergence happening at different rates. I mean, when you look at the Fourier series with one term, two terms, three terms, four terms, you can kind of see that the blue function is converging to the red function. Okay, the blue function values are converging to the red function values before you rise. But as you increase the number of terms, let's go up to 10 terms here, you start to notice something. Because you start to notice that for most values, the convergence has become quite good, or quite close there. For most values of x in the domain, the Fourier series is doing a fair good job. It's just oscillating tightly around the red function. But when the argument x gets close to 0, the convergence kind of gets a bit worse. You see larger and larger oscillations away from the red function as you get closer and closer to 0. And this becomes even more pronounced when you increase the number of terms. We jump up to 17 terms, say. Okay, we continue to see very good convergence happening for most values of x. But there seems to be something funny going on near the point of 0. Now, the point 0 is special for this function because the point 0 is the point of discontinuity of the function. And the Fourier series, I mean, even if you bump it up to a huge amount of terms, 40 terms, 39 terms, might take a while to evaluate that. So now, for all intents and purposes, at this zoom level, the blue function is kind of equal to the red function, as close as you can see, except where you start to get close to these points of discontinuity. There, the convergence is still lagging behind. This behavior has got a name. It was kind of discovered or noticed by people in various settings, but the name that's become kind of attached to it is Gibbs phenomenon. So this is the Gibbs phenomenon near points of discontinuity. One way to think about it is that you're kind of asking, remember, the Fourier series is constructed out of cosine and sine functions. Those are functions that are continuous across the interval. The sine function and the cosine function, they're both continuous at 0. But we're trying to get them to converge, or we're trying to get a series made out of them to converge to a discontinuous function, the red function. You're kind of asking continuous things to approximate better and better a discontinuous thing. That's kind of asking a lot. So the Fourier series, you can't kind of get away from this large deviation. Now, this function is still converging pointwise to the red function. This sequence of Fourier series approximations are still converging to the red function pointwise. So if you pick any particular x, even if you pick an x value close to x equals 0, so although we're seeing large deviations there now, so if I pick a point close where the mouse pointer is here, very close to 0, although you see a large variation of the blue Fourier series away from the red function, if you increase the number of terms vastly, while the Gibbs phenomenon, the wobble will still be there, it will have moved a lot tighter to the point of discontinuity. Okay? If you keep on increasing the number of terms, those waves that happen near the point of discontinuity are getting squashed closer and closer to the origin x equals 0, to the point of discontinuity. Okay. So if you waited around long enough or added enough terms to the Fourier series, you would eventually see very good agreement with the function at any particular point that you desired. There would still be the large variation, the large Gibbs phenomenon variation at points closer to the origin. But then if you picked any particular point closer to the origin, just waited around a lot more to see more and more terms added to the Fourier series approximation, you'd eventually see the convergence get as good as you want there as well. This phenomenon has been likened, or it's been kind of, a good kind of way to think about it, or a thought experiment. You'd be familiar with the idea of riding a bike. Now, if I asked you to cycle your bike down this way and make a severe hard turn to the left. So imagine yourself cycling fast and being required, if the road makes a 90-degree, a sharp turn to the left. If you watch yourself doing this the next time you're on a bike, or watch a person on a bike doing it, what you notice is that in order to make a severe turn to the left, what you end up doing is right before you make the severe turn to the left, you kind of curve to the right a little bit. You kind of curve to the right a little bit, and that enables you to make a tighter turn to the left at the point where you have to make the turn to the left. And the effect becomes pronounced as the speed of the bike increases, the effect becomes more pronounced. You can't just cycle in a straight line and immediately turn to the left and still stay on your bike. In order to achieve it, it requires a wobble or a swerve to the right first, and then you can come around and make a sharp turn to the left. Okay? So this notion of Gibbs phenomenon has been likened to that, or associated to that. Because what you're asking the continuous sine and cosine functions to do is to suddenly, as you're coming along here at 0, we're asking them to suddenly change from being 0 to being 1 up there. Well, that's a very severe change you're asking a continuous function to do. So you can see the function in almost, you can think of it as that in preparation to make this extreme jump in value, it has to start making little variations in value until it's ready to jump up to the level x equals 1. Okay. So this is pointwise convergence. The convergence happens at every point in the domain, but it can happen at different speeds at different points in the domain. So here, points near in the middle here, the convergence is quite good, but points close to 0, the convergence is less good. Now, the other type of convergence, uniform convergence, is where that different rates, or that the convergence happening at different speeds where that has been ironed out. So this is uniform convergence. So we're still referring to this setting of having a sequence of functions fm converging to a limit function f. So it's still true that at each value x in the domain, that the sequence of function values fm of x converge to f of x as m tends to infinity. But now we have an extra condition. Before, this convergence was allowed to happen at different rates. There was no extra condition which said how fast it had to be converging over here compared to how fast it was converging at some other location. Okay, but now we make the extra stipulation. And moreover, this convergence happens at a uniform rate across the domain. Well, that statement in itself is maybe a little bit vague and maybe not exactly matching what it is, but we'll put down the formal definition. The formal definition looks a lot like the formal definition of pointwise convergence, except you'll notice a crucial difference. And the crucial difference is in the placement of the quantifiers. So we still want the function value fm of x to be getting within a distance epsilon of f of x. And we still want this to be so for every m greater than or equal to some point capital N. And we still want to be able to do this for every epsilon. But the key point now is in the placement of the quantifiers. The quantifiers get placed in this order. See, before the universal quantifier for all x was to the left of there exists an m. So that allowed there to be different m's for different x's. Because you could imagine this m, say, would have a subscript of a x on it. So for different values of x here, you could be talking about different, sorry, there's just a lot of chatter there. We could be talking about different points capital M. Whereas here, this condition is saying, well, for every value of epsilon, for every for every tightness of convergence that you talk about, there is one point, capital M, in the series of functions. And across the whole domain, for every value of x, once you pass this point, capital M, in the sequence of functions, for every value in the domain, then, we have this good agreement, this tight agreement to distance epsilon between the function values of the sequence functions with the limiting function. Okay. So it's this very small change in the formal definition, just the change in position of these quantifiers. Exists M and the for all x. When they're this way round, it's uniform convergence. It's the other way around, non-uniform convergence. So this example of the square wave function Fourier series this exhibits non-uniform convergence. just keep the chatter down a bit. That was one of the things raised by the student reps at the staff-student liaison committee. I accept it's late in the afternoon. You've been in class a long time, but try to keep it down. Thank you. Yeah, so what we can see in front of our eyes here with this Fourier series is non-uniform convergence, okay? Because this Gibbs phenomenon is kind of always going to be around. Even if we whack it up to 100 terms, I hope you'll still be able to perceive it here. Even if you look very far down the sequence of Fourier series approximations, hopefully this is going to appear, the Gibbs phenomenon wobble will have moved will moved extremely close to x equals 0, but it's still going to be there. Okay? It's still going to be there. So if we were looking, let's say our epsilon was small and less than the distance of this Gibbs wobble here. Okay? That would mean that there was no single large m value, for which the Fourier series function would be close enough to the square wave function for every point in the domain. Okay? So even for this point, at 100 terms or 96 terms in the Fourier series, we've got extremely tight, good convergence at most of the points in the domain. But there are still some points in the domain that are lagging behind, the points close to the points of discontinuity. Their convergence is not at the same rate as the convergence everywhere else in the domain. Okay? So that's the crucial difference between uniform convergence and non-uniform convergence. Okay? Uniform convergence is much nicer. You don't have this Gibbs phenomenon. Okay? You've got convergence happening at the same speed or a kind of at bounded speed across the whole domain. That's a better way of saying it. Rather than saying at the same uniform rate across the domain, rather you could say at a bounded rate across the domain. Okay. Now, how does this relate to the differentiation of the Fourier series term by term? Well, being uniformly convergent is a condition that allows you to differentiate term by term. Okay. So you can see here this paragraph here, the bottom just before theorem 3.6, term by term differentiation or integration of an infinite series of functions is valid if the series is converging uniformly. Okay. But if it's not converging uniformly, then it isn't a valid step to assume that you can differentiate it or integrate it term by term. Now, theorem 3.6 gives us some conditions under which the Fourier series converges uniformly to the limit function. These aren't necessary conditions, but they are sufficient conditions. So the conditions given here in 3.6 are enough to ensure that the Fourier series converges uniformly. But there can be functions which still converge uniformly, even though some of these conditions aren't necessarily true. So let's have a look at these conditions, and you should be able to see why this condition is not satisfied by the square wave function we were just looking at. Okay? So this says the Fourier series of the function f over the interval minus pi to pi, it is uniformly convergent if the following conditions hold. So the following conditions are that the function has to be continuous. Okay, so straight away you can see that our square wave function broke that condition. So the square wave function is not continuous over the interval. The first derivative of the function has to be piecewise convergent. So that allows you to have non-smooth points. So points where the function takes an instantaneous change in direction. So kind of sharp points in the curve of the function. Because there, the derivative is not continuous. The derivative makes a sudden jump in value. So the function is allowed to have, kind of sharp points in its graph. And lastly, the function must be periodic of period 2 pi. Now, that last condition means that the function has to agree at the endpoints at minus pi and pi. That's another reason why the square wave function violates these conditions, because at the left edge, at x equals minus pi, the square wave function was -1, whereas at the right-hand side at x equals pi, it was +1. Okay? That's where the point of discontinuity happened again. Okay? But under these conditions, the convergence will be uniform, and you are allowed to differentiate or integrate the function term by term. And this gives us a nice application in something called Parseval's theorem. Parseval's theorem is a theorem about what you get kind of when you add up all the Fourier series coefficients themselves. It's like a sum of squares type formula. And it can be related quite nicely back to the linear algebra concepts of norm and magnitude of the vector. So when I see you later on in an hour's time, I'm going to do some examples, but we'll start by giving a proof of this theorem 3.7. So it's really just an example of an application of this uniformly convergent condition. This term on the left, the integral of the square of the function, that's like when you think about the inner product used on functions here, that term on the left is like a square of a magnitude type measure on a vector. And here on the right-hand side, we have the sum of squares, more or less, the sum of squares of the components of the vector, or the sum of squares of the components of the Fourier series. So it links nicely to the idea you have from simple geometric vectors that the square of the magnitude of the vector is the sum of the squares of the vector's components with respect to orthonormal basis, or the standard basis, if you like. Okay, so we'll discuss that theorem. That only takes a few minutes to prove that. We'll discuss that at the head of the next hour. What I see with 4 or 5. And we'll do the example following it and pick up another few examples as well. Okay, so I'll see you then.